Okay. All right. Well, so week 2, and we'll get into chapter 3. Okay. So Intro to Statistical Learning with R, chapter 3, from the textbook. In this textbook, chapter 3 is a very long chapter, and it pretty much summarizes all of Stats 101A in chapter 3. Okay. And so I don't know when you took 101A. It might have been just a couple quarters ago, or it might have been longer ago. I'm not sure. But chapter 3 basically summarizes, I think, pretty much all of 101A. You know, it talks about a lot of these things, and so we'll go through it. And we'll start applying some of the tidy modeling techniques to it as well. Okay, so we'll start off by looking at simple linear regression, and then we'll expand and move to multiple linear regression. All right. Oops. Okay. So the example that we're going to use comes from this data set on advertising data, and the question is, how effective? You know, what's the relationship between money spent on advertising and the amount of sales in a particular region? So, you know, I guess we're looking at different markets, and in some markets we spend money on TV, some markets we spend money on radio, and some markets we spend money on newspaper ads. You know, this is a little bit of an older data set. These days you would look at, you know, spending advertising on YouTube versus Facebook versus Instagram, or, you know, different kind of platforms and things like that as far as your ads, or maybe you would just put internet advertising and things like that. Okay, but this is the thing, right? So newspaper advertising, you know, who looks at the newspapers and reads those ads anymore? But you know, TV and radio, sure, those still exist, and you know, now it'd be like instead of radio, it'd be like podcast ads, right? You know, get a new mattress or whatever. I don't know what these things are. Okay, so anyway, here are linear regression models that we have created. Simple linear regression models between sales and each of the 3 mediums. Okay, so we can see there's a model for TV, a model for radio, a model for newspaper, and things like that. And you know, right off the bat, we see some issues. You know, so here we're assuming a linear relationship, but you know, I'd say we see a lot of kind of heteroscedasticity in terms of like the amount of spread not being the same, and things like that. But again, you know, all of life is a bunch of compromises, and statistical analysis is no different. And so you know, from a theoretic standpoint, a lot of our assumptions about, you know, these models are, you know, we assume that the error is normally distributed with a constant variance and things like that. And, you know, probably when you fit a model, that won't necessarily be the case. But is the model still useful? Is it still helpful? In a lot of cases, the answer is going to be yes. Okay, and so we can still kind of continue while acknowledging that, you know, we're not trying to do some kind of theoretic work where all of our assumptions need to be met, but just kind of from a practical standpoint, is this, you know, a useful way to think about it? Okay, and so these are a bunch of questions that the book poses that we could try to answer using linear regression analysis. And so, you know, overall, is there a relationship between the advertising budget and sales? So, you know, between any of those, any or all, or some combination of those 3 mediums and sales, and it looks like overall, the more you spend on ads, the more sales you make. And a lot of times we feel, I think if you ask people on the street, are you affected by advertising? A lot of people will deny that they are. But the truth is people are affected because it can be shown that, the more money you spend on ads, the more that happens in sales. And so, we are constantly bombarded by advertisements. And we could probably think about a few times in our life where we're like, oh yeah, this ad made a difference, right? When I saw this ad as a kid, I wanted that toy. Or sometimes I'm watching some video or thing and there's an advertisement for food and I go, oh yeah, I kind of want to eat that, right? And so we can probably pinpoint a few times where these things are effective. And even if like 95%, 98% of ads don't affect us, even if it's just 2% that do, that 2% makes a difference, okay? And probably a lot of these things actually affect us a little bit more than we'd like to admit, right? Just kind of establishing, I don't know, some cultural thought and stuff. Okay, so not only is there a relationship, but how strong is that relationship? We want to know which ones, which forms of media contribute to sales and things like that. And can we, figure out the effect? Can we predict future sales? Is the relationship linear? And is there an interaction effect between advertising media, right? Is there, I guess you could call it a synergy, but basically, is the combined effect of TV and radio more effective than just TV by itself plus radio by itself? Like, do they somehow combine together and improve things even more, or do they actually work against each other? These are all kinds of questions that we might be able to answer with linear regression. We'll first start off with simple linear regression. And simple linear regression, this is covered in your Stats 10, your introductory stats class. And basically we have one predictor, one X variable going in, and we're trying to predict our output Y, and we say, the relationship between X and Y is linear, and a straight line is defined by a slope and an intercept, and so it comes down to estimating what is the intercept, what is beta 0, what is the slope, beta 1, okay? And the key thing about linear is that throughout the entire range of X, a change of 1 here has the same effect as a change of 1 later on, okay? And so we're saying if you go from spending $2 to $3, okay, that's going to have the same effect as going from $2,000 to $2,001, okay? And we're saying, by adding 1, the amount that it affects Y is going to be the same. And so, things like what is the weight of a stack of paper or something like that, right? So if you go from 2 sheets to 3 sheets, how much does that stack of paper change weight? Well, it's going to be the same as going from 2,000 sheets of paper to 2,001 sheets of paper, okay? Add every additional sheet of paper you add is going to increase the weight by that same amount, okay? And so that would be a linear relationship. Whereas a lot of other things in life don't have that same kind of linear relationship, right? If you think about someone's height, okay? Someone going from age 2 to age 3, how much did they grow, okay? From age 2 to age 3 is not going to be the same as somebody going from age 32 to age 33, right? How much did somebody grow from age 32 to 33? Probably 0, okay? Whereas if you have a child that grows 0 from age 2 to age 3, that's a serious issue, and so that that would not be linear. Linear just says the change in X has the same effect on Y, and specifically it's going to change by beta 1, okay? And it's going to hold true when X is little. It's going to hold true when X is big. Now, a lot of things in life don't follow this, but we could say within this range, of x, the relationship is linear. So we could say, you know, height, the change in height, you know, based on each year, that's linear from age 2 to age 15 or something like that. You know, someone going from age 2 to age 3, we expect to be about the same. Going from age 4 to age 5, expect the same to be about age 12 to age 13. And, you know, we have growth spurts and things like that, but we might be able to say overall that period is linear. Outside of that, no longer linear, stuff like that, okay? We fit our model, and we're gonna get y hat, our estimate, is going to be whatever our estimated intercept is, our beta 0 hat, and our estimated slope. Beta, is this beta hat 1 or beta 1 hat? I don't know. Whatever this value is, right? So these are the values that we estimate, our parameter estimates. And you know, how do we estimate these things? Well, we estimate them using the least squares criterion. The least squares criterion says we want to minimize the residual sum of squares. So if we say each residual is the difference between the actual value and our predicted value, okay, the residual is the difference between yi minus our prediction is this, you know, our intercept and slope times our x. And we're going to calculate this for every single value in our data set. We square all of those residuals, we add them all up. So if we expand that out, you know, we're going to get this, and we say, you know, what is the beta 0 and the beta 1? What values should we estimate to minimize this quantity, RSS, right? And have you guys taken 100C or whatever? In 100C, you work through all of this and you show, you know, this is how you minimize it. I don't know, do you minimize it in 101A as well? Not mathematically, right? But in 100C you do, okay? And anyway, the picture, you know, looks something like this, okay? So the red dots are the actual values. The blue line represents what we are estimating, the estimated line, okay? And so this line is determined by our slope and our intercept that we have chosen. And we want to measure what is these vertical lines here is the residual between what we predicted and what it actually was, okay? And so we can see for some of these things, you know, for around 50, however, you know, when we spent 50 on TV and the amount of sales was, you know, we predicted, I don't know what number this is, 9, okay? And the actual value was 8 or whatever, you know, there's not a huge difference between the line and what we predicted. Whereas over here, you know, we spent 270 or something. We predicted 19, 18, 19, something around here. And in reality, this observation was like 12. And you know, what's frustrating is that we have another market where we spent the same exact amount on TV and their actual value is like 26, okay? And so sometimes that happens, right? You put the same amount into this, and then this one was like super productive, and this one wasn't, and you know, overall, you just say, okay, well, the true answer is probably somewhere in between. And anyway, this line is the one that minimizes the total of the squared residuals, okay? And you know, you could kind of go through some work and calculus to say, okay, well, how do we figure out and minimize this? Well, your estimated slope can be found by, you know, basically taking this thing, okay, and I guess you also maybe did this in 100B or something, or you know, another common thing is, you know, standard deviation of y divided by the standard deviation of x multiplied by the correlation, and you know, this is kind of part of your covariance values here. And then the intercept is such that the line always runs through the point x bar comma y bar. This diagram here, okay, this diagram here shows a contour plot of the RSS for different values of beta 0 and beta 1, okay? So the value that minimizes the RSS is when beta 0 is equal to 7.03 and the slope, beta 1, is equal to 0.0475. And if we were to pick any other value for beta 0, okay, this is maybe like a 3D plot. It looks kind of like, you can imagine this elliptical bowl shape, okay? This elliptical bowl shape. And the two axes is, one is the intercept and one is the slope. So we're saying if I had chosen a different line, here's a, let me illustrate with this. Okay, so here is, this is a different data set. Okay, but this red line represents maybe our line of fit, and the values in our data set are these different colored dots, blue, orange, green, and stuff. And what you see here, this is the squared residual. So we are taking the vertical distance between each dot to the vertical line to the vertical distance to the line. Okay, so this purple dot, which is really close, has a very small residual, and we can see it has a very small squared residual here. This brown dot is kind of far away from the line, and so we get a much bigger squared residual. And what we're saying is that right now our intercept is 0 and our slope is 1. And we're saying, well, what if I slide I can change what my intercept is, which is basically effectively sliding this line up and down, okay? And so, you know, I don't know what the minimum is, but we can see that if I take the intercept and I make it too small, what happens? Okay, here, wait, let's move the intercept so it's right on going through that brown line. Okay, when we do that, we see, okay, you know, there's no pretty much no squared residual for the brown dot, but now I've got these huge residuals for the orange and the green dots. Okay, and so the total sum of squared residuals is huge, right? What if I move it the other way? Okay, well, I can move it up here and have the line basically pass through the orange and green dots. And so I have very tiny squared residuals, but now I'm super far away from the brown dot, and so when I square that, I have this, right? And so probably the true answer is somewhere in between here. And this is what we're saying. You know, this plot is showing that as you change your beta 0 to be too big, your squared residuals go up, okay? So the minimum is around here, 2.11. As I move to the right, it goes to 2.15, 2.2, 2.3, 2.5 as I move this way, okay? And if I move the beta 0 too small, you know, I start climbing up the contours of this plot as well. Similarly, I can change the slope, okay? And so I could change the slope to be something like this. And overall, the relationship is you kind of have this negative relationship between slope and an intercept for to try to kind of keep a certain amount of, like, if we wanted to keep this, right, I can make the line steeper, but if I make it steeper, what do I have to do? I have to bring the intercept lower, okay? Whereas if I make the slope shallower, I have to raise up the intercept, okay? And so, and you know, we can kind of fiddle around with these things trying to figure out what is the best intercept and slope to use that's going to minimize the squares of these residuals. And what we see, you know, we also see that, you know, I could change the slope, increase it or decrease it, and that's going to change the amount of residuals. And overall, if I increase the slope, okay, to kind of end up in a lower zone, I have to decrease my intercept, or if I make my slope more shallow, I have to increase my intercept, which is kind of what we saw, at least if your data exists in this first quadrant here. Okay, so that's what this diagram represents. It represents the contours of the total, you know, residual sum of squares for different values of beta 0 and beta 1. Okay, and so, you know, what we do is we pick the beta 0 and beta 1 that minimizes that sum of squares, residual sum of squares. Let me go ahead and give you your first view quiz answer. letter D. D as in dog is your first view quiz answer. D. D as in dog. Now, when we fit our a regression line to our data, okay, one thing we want to do is we want to acknowledge the fact that the sample of data we have is just one random sample that could have been generated from this population, right? So we could imagine there is actually some true relationship between X and Y in the population, okay? And that if we were able to measure every single individual in the population, we would get the true slope and the true intercept that exists for this linear relationship between X and Y. Of course, there's going to be random error and things like that, but there might be some true slope, some true intercept. What we are doing is we're trying to estimate what that slope and what that intercept is based on the sample of data we have, okay? But our sample of data is random. And so maybe we happened to get too many values that will increase, that seem to show there's a really strong relationship between X and Y, right? Maybe in our random sample we happen to have markets where the people really respond to the TV advertising, so we show this strong, big slope, okay? Or maybe by random chance we end up selecting the markets where people are kind of immune to the radio advertising. They don't, just by random chance, right? When we do this, and so if somebody were to get another random data set, it's drawn from the same population, but they get a different random data set, and they fit a line, their slope and their intercept will vary from our slope and our intercept, right? And this is kind of where the bias variance trade-off comes in. And so, the linear regression line generally has lower variance in as far as our models go, if it's a simple linear regression line. And so we can kind of get an idea of how much will our lines vary by using some kind of simulated situation, some kind of simulated population. And that's what these charts are supposed to represent, okay? So this left plot is one data set, okay? One data set that we've generated around the true relationship. So the true relationship is represented by this red line, okay? The true relationship between X and Y in the population is represented by the red line. And the dots, the random dots, have been generated via, using random noise around the red line, okay? And in this particular data set, okay, these are the dots we got, and if we say, all right, fit a least squares regression line to the dots, we end up getting this blue line, okay? And so this blue line has a slope that's a little bit higher than what the actual true red line is, and its intercept is going to be probably a tiny bit lower than what the true line is, okay? So we see the estimated line in blue isn't exactly the same as the true line in red, okay? And over here, this shows a bunch of estimated lines. And so we just have to pretend that some other random data set showed up and we estimated the line that fits that data, right? And we did this maybe like 20 different times or something. I don't know, maybe 10 different times. I don't know how many. Can you guys see the light blue lines here? Okay, so these light blue lines represent, okay, what are some other slope and intercepts that we've estimated from other random data, okay? So again, we're generating our data around, we're simulating data around the true line in red, and we're saying, okay, what other slopes and intercepts have we created? And so we can see this. And we can see overall, if you were to average all of these light blue and even the dark blue lines, if you were to average them all, and you say, okay, what's the average slope? It's probably right around the slope of the red line. And what's the intercept if you average all of these things? Okay, if you average all of the intercepts, you're probably going to get something right around the true intercept of the red line as well. Okay, so all of these lines are a little bit different from each other, but if you were to average them all, you'd get something pretty close to what this red line is, right? And so that's the idea that the least squares regression line is unbiased. Where do you guys talk about the BLUE, the best linear unbiased estimator? The blue, yeah. But which class is that?
Econ.
Econ, what? No, 100C? Okay, all right. So if you've taken 100C, it's, you learn about this being the blue. It's not covered in 101A, the blue, concept of the blue? Okay, all right. Well, anyway. And if you haven't taken 100C, no worries. It's not required to take this class. But it's the idea that as far as, well, this is the unbiased part in the blue, in that if there is a true line, then when you do least squares regression, you get a whole bunch of these different lines, and the expectation, the average in the long run, every time you fit a different linear regression line in the long run, when you average them all, it's going to be the true value, right? It's unbiased, okay? Whereas, we'll learn about shrinkage methods and other things, in the coming weeks, where the expectation is not the true value. Yeah?
So you're resampling the population every time fitting a linear model?
This is a simulation. We would not do this in real life. But yes, in this simulation, we are resampling data points from the population, and every time we're fitting a new linear regression line.
How would that be different from just basically getting a larger sample size and fitting a linear model to that instead?
Yeah, so in real life, you have one sample, and if you say I've got more money and I can collect more data, you would just combine it into one larger sample. Okay, this simulation, is to kind of illustrate or study the idea that how reliable is my slope and intercept estimate going to be based on one sample, okay? And if I had gotten a different sample, what would I have gotten, right? Because in real life, you only get one sample. And you wouldn't do this dumb thing of like chopping it up into things and saying, hey, let's fit a linear thing over to this, subset. You just have one big sample and say, I spent all of my money, all of my research grant gathering this data, and let's analyze it. You wouldn't intentionally, do something funny with it. But you want to know how reliable is this, is my slope? How reliable is my intercept estimates? And this gives us an idea. So we can kind of simulate a similar situation, and we can say, okay, well, this gives us an idea of how much variance our slope might exhibit, how much variance our intercept might exhibit, okay? So yeah, for any one given random sample, we can't expect our least squares regression line to exactly equal the population regression line, okay? Because it's subject to random noise. But in the long run, we can expect the average of all of these fitted regression lines to be equal to the population regression line, okay? That's the idea of the long run. Now, of course, any one individual or any one random sample is not going to be the case. But that gives us hope, because in the long run, we expect it to be unbiased, okay? So that's what we have, okay? But we don't know. And so we can ask, well, what is the variance around our estimates, right? How much does the slope vary from one random sample to another? How much does the intercept vary from one random sample to another? And this gives us we can get standard errors around these coefficient estimates, right? So we can say, okay, well, if somebody else gets a random sample and somebody else gets a random sample, if we produced this sampling distribution, okay, so if I repeated this process like infinitely many times, and I measured every single different slope I get and every single different intercept I get, what is the standard error there, right? What's the standard deviation of that sampling distribution of all the different slopes? What's the standard deviation of all the that sampling distribution of all of the different intercepts? That's the standard error. I'm not going to try to derive or prove this or something. I think this, again, covered in 100C or whatever. That's a different class, but the concept. Okay, so I'm not too worried about this actual formula here. All right, but the idea that your slope exhibits variance and the idea that your intercept exhibits variance and has its own kind of standard error, that's the important part. Okay, and what do we see in here? We see that the variance of the data itself plays a key role. Okay, so if we had to estimate, this is a ridiculous thing, okay? But imagine a whole, you're trying to estimate the weight of, I don't know, a room full of dogs or something, okay? So, you have a room with, 5 dogs versus a room with 50 dogs versus a room with, 100 dogs. And just say, hey, let's estimate how much all of the animals weigh based on how many dogs are in the room, okay? Well, dogs have a high variance, right? You could have, dogs are one of those, I don't know how many other species exhibit this much variance, right? Where you can have little dogs and you can have big dogs, and they're both dogs, and you can mate breeds from different, totally different breeds, even despite huge size differences and stuff, and so you got this huge variance, and so how confident are you going to be in your slope estimate? Okay. Probably not, unless you have a huge sample, which we'll get into as well. Your estimate of your slope or whatever, the amount of variance there is going to more variance, bigger variation in the slope. Okay, whereas on the other hand, what if we said, okay, estimate how much a stack of pennies will weigh? Okay, based on how many pennies. All right, here I've got a stack of 5 pennies. Here I have a stack of 50 pennies. Here I have a stack of 100 pennies. Guess how much this thing weighs? Okay, you can probably get a very accurate estimate, okay, on how much that stack will weigh based on how many pennies there are. Okay, now not every single penny weighs exactly the same because over time, metal rubs away and stuff like that. But you can probably get estimated very, to the 10th or even 100th of a gram of accuracy there. You can get very, very precise estimates. Okay, and that's because there's not going to be very much variance from one coin to the next, right? Maybe if you went back centuries and you had like those old Roman coins where, we see that they're all different sizes and stuff, that would have more variance. Okay, another thing, notice for the standard error for the slope, okay, in the bottom we have kind of this sum of squares for x, sum of squared distances from the mean, right? So this is kind of like how far is each x value from x bar. So it's kind of like almost like the variance of x, and that plays a relationship. And this, and I wanted to kind of illustrate this. And the idea is, if you only have a small range of x values, then your estimates of the slope could vary quite a bit, right? If you're only trying to estimate, how much is the slope, and you only have rooms where you have like 10 dogs versus 11 dogs versus 12 dogs or something like that, the distance between your max x and your smallest x is quite small, right? And so your you might have like 5 rooms with 10 dogs, 5 rooms with 12 dogs, and you might try to get some kind of estimate there, but it's probably going to be wildly off. Whereas if you have a room with 5 dogs and then a room with 100 dogs, okay, and you have a huge range of x, you can get more confident estimates of your slope. So here are just some random points where x is spread out. You can kind of, because you have such a wide range for x, you can be a lot more confident in your slope estimate, okay? And so we can see that the standard error of the slope is smaller if the xi's are more spread out, right? As each kind of those points have more leverage. Okay, so that's this concept of standard errors for our coefficient estimates. And anytime you have a standard error, okay, you have a sampling distribution, you can then perform inference, and you can also, so that includes things like a confidence interval. So you can create a confidence interval for your slope and a confidence interval for your intercept, okay? And your confidence intervals are roughly 2 standard errors up or down. That's for a 95% confidence interval. And we can then also perform a statistical test, right? So we have a standard error for the slope, and we can say, ask the question, is my slope significantly different from 0? Okay, we have a standard error for the intercept. Is my intercept significantly different from 0? So we can now perform a hypothesis test, right? So if my slope is 0.02, is that significantly different from 0? Well, it depends on my standard error. If my standard error is 0.05, 0.02 is not significantly different from 0. On the other hand, if I have a slope of 0.02 and my standard error is less than 0.01, then I guess 0.01 would be right around, it's barely significant. But if I have a standard error that's less than 0.01, then that slope of 0.02 will be significantly different from 0. Okay, so having a standard error allows us to then perform statistical inference, right? And so we can kind of ask, is my slope equal to 0? That's going to be my null hypothesis. Right? There's no relationship between x and y. Bumping up x should not have an impact on y, whereas the alternative is that there is a slope that is not 0. Okay, and so we do this, and we can calculate a test statistic t. Right? We take our current slope, we say how different is it from 0, so subtracting out 0, and then we divide that slope by the standard error of the slope. And if this thing, in general comes in something a little bit bigger than 2, t distribution, so maybe it has to be more significant if we only have a couple degrees of freedom, things like that. But in general, if you get a slope that is, rule of thumb, more than 2 standard errors away, it might be significant, versus it might not be. Okay. So if we reject the null hypothesis, we would say we have evidence that there is a relationship between x and y, and if we don't, then we don't. And so this is kind of the result that you get when you take, so here I load up the data, and we're going to predict sales based on TV. And I get, I use LM, predict sales based on TV, and I call summary on the model, and this is what we get, right? My estimate of the slope is 0.047, and my standard error on the slope is 0.00269. So it's this very tiny standard error, and therefore my test statistic t is like 17. Okay. So, in rule of thumb, if your t is more than 2, okay, and if you have very few degrees of freedom, then you might need a t of like 3. But rule of thumb. If you have a high number of degrees of freedom, lots of data, you only need a t of around 2. We're getting a t of 17.6 standard errors away from the mean. So we calculated p-value. We get practically 0. Okay, the probability of getting this kind of slope by random chance, right? So that's what our hypothesis tests do. We're asking, what's the probability that just by random chance I happen to get this slope? And it says, well, with the amount of data you have, it's very, your slope is 0.047, which we might say, like, oh, that's not huge. But compared to the standard error and stuff, it is significantly different from 0. And so we would say the probability of getting this by random chance, that probability is practically 0. Okay, and so we get, the 3 stars. And that's what we do this. And we can also do the same kind of question. What's the probability that my intercept is different from, not the probability, what's hypothesis test is 7 significantly different from 0? And the answer is yes, it is. And that's what we have here. Okay, I want to just talk about using tidymodels. Okay, so this is assuming we've loaded library tidymodels. And let me just kind of flip from the lines of code that we have here to this. Okay, so over here, when you use tidymodels to create a linear model, there's more lines of code involved. Okay, it's a little bit of a cheat here. It says like, oh, it looks only like there's 3 lines. There's more lines of code because over here there's really only just 2 lines creating the model over here, and these 2 lines up here are loading in the data. So here the data is already loaded, and we're going to use one of our first commands. After you do library tidymodels to load tidymodels in the first place, one of your first commands that you might want to use, or is recommended to use, is to call tidymodels prefer. Tidymodels prefer. And what does that mean? Well, in R, you can name a lot of functions or name objects to whatever you want. And I don't know if you've ever done this mistake where you name a function or an object C or something like that, and then it breaks things later on, because in R, that function C is very important for like creating vectors. So anyway, tidymodels prefer just says, hey, if there's a conflict, like if there's some function name and it appears in tidymodels and it appears in some other thing, use the tidymodels function. Okay, so it just kind of says if if you have two things that have the same name, I'm talking about the tidymodels one. Okay, all right. So in tidymodels, the way it works, and it's quite different from using LM. LM, you just say, all right, predict this based on this. You give it the formula and it creates the linear model. Here you have to do a few things. One is first you define a model, and then once you have the model defined, you run a fit function on it. You say, take that model and fit this data. And then once you have fit that, then you can work with it. And in some cases, you have to extract the fit engine and things like that. So the first thing we're going to do is we're going to start off by creating a linear regression model. Linear regression model in tidymodels. This is called a parsnip model. Okay, a parsnip model is the linear regression model. Why is it called parsnip? Well, parsnip. So there used to be a function library called caret, and this is like a play on words because parsnips are vegetables that are kind of like carrots, whereas the library caret it was spelled more like the symbol above the number 6 on your keypad. But anyway, play on that. And I think it's also so you have parsnip, which is also reminiscent of the word parsimonious, which kind of means like you don't have to use too many words, but you end up using a lot of words and stuff. Anyway, okay, so you set up a linear regression model. Now, the reason why we like to do tidy models, or the reason why I'm keep pushing for this, is that tidy models allows us to interact with a bunch of different modeling engines, okay? And so in the great debate between R and Python, okay, one of the biggest kind of philosophical differences between the languages is that when it comes to things like machine learning, in Python there's really just one package, and that's sklearn for machine learning. I don't want to say just one package, because as for deep learning, there's like competing things. You've got TensorFlow and PyTorch and things like that. But for machine learning, the biggest package that you're going to use is sklearn, and it encompasses a whole bunch of models, and sklearn just keeps kind of growing and stuff, and there's kind of a development team behind that. On the other hand, with R, you can find, maybe like 5 different models that perform similar things, or have, kind of similar end goals that approach it, slightly differently, okay? And so for even something like creating a linear regression model, okay, a linear model, we have the base R LM way to create a linear model. But then there's other ones that kind of incorporate, Bayesian statistics and things like that. And you got Stan, and you have this and that, and you got all of these different things, okay? And one of the troubling aspects, or I don't want to say troubling, okay, because this is like it's a great thing, but it's also a frustrating thing, right? It's kind of like, is it better to have, in Europe, you have a whole bunch of people speaking a whole bunch of different languages and stuff, okay? Versus, in other countries, it's like just one language, right? And so one of the things that could, become a little bit frustrating, or a little bit, requires some thinking, is that when you interact with these different packages in R, you have to learn like that package's particular syntax and that package's particular argument names and all of these things, right? So there's like several packages that do like random forest, okay? And some of these random forest packages will say, okay, the number of trees is n trees, and the number, something else will call it something else, and they got all these different things for basically talking about the same stuff. So what Parsnip does is it allows you to interact with all of these different engines using a kind of a consistent syntax. Okay. Now, for something like LM, it feels like there's a lot of overhead for something simple. But if we understand, if we start getting used to the tidy model syntax, then we can start interacting with a whole bunch of other packages without much more difficulty. Whereas without tidy models, it gets a lot more messy. So anyway, we're going to create a linear regression model, and we're going to just use the base R's LM engine for creating this thing. Okay, and then again, you can kind of adapt this to use different engines as well. Okay, so now that we have this model defined, we want to fit the model to the data. So we take LM and we use the pipe, and we say fit data onto the model. Okay, so we're going to say fit, and we give it the formula, predict sales based on TV using the advertising data. Okay, and so we run fit on this, and we store it into basically a model fit object. In this case, we're going to call it linear model formula form fit, meaning the formula fit. Tidy models allows us to fit data using the formula style, and it also allows us to use kind of this matrix style XY, which is more prevalent in say Python's sklearn. Sklearn, you fit the data using the XY matrix style, and I guess I can show examples of that another day, but not today. Okay, and then once we have the formula fit, if we wanted to use something like summary, we have to extract the fit and then call summary on that extracted fit. Okay, so here I'd say take that fitted object, extract the fit, and apply summary. And we can see the results here are pretty much exactly the same. Here the call is lm, and here only this part changes, but the summary output is exactly the same. Okay. So just to kind of summarize, and I posted a homework 2, and in homework 2 you have to read, chapters 6 and 7 in the tidymodels textbook, and that will kind of lead you through how to fit a model in using tidymodels. Okay, so you got to specify the model in the model engine, you fit that model to the data, and then from there you extract the detailed information, desired information from the fitted model. Okay, and it's going to feel cumbersome when you're doing this for simple linear models, right? So if you know you're only going to fit a linear model, then tidymodels probably isn't worth it. And I force you to use it for this first homework, or this homework that I've created. But if you know you're just going to stick with linear models, it's probably not worth it. But if you're going to fit a variety of models, okay, then tidymodels is definitely going to be worth it. And so, I'm still kind of writing up rubrics and stuff and instructions for this Kaggle competition that you guys are going to be participating in. And I see people trying to find groups, which is great. And I do want you guys to start thinking about groups that you're going to be working in, groups of 3 or 4. And you will want to fit a variety of models, okay? And so I think tidymodels, you'll find that to be, anytime you start something new, there's a frustrating learning curve, right? But then once you are able to use it, it's great, right? It's like driving, right? When you first start out driving, it feels like it can be a little overwhelming, okay? But then once you're able to drive, you can't imagine life without being able to drive, right? To get to have that convenience of getting from one place to another, or something like that, right? Or I don't know, maybe not a great example, but or it's like teaching your grandma how to use their iPhone or something. You'd say, this is going to make your life better. And maybe they want to learn it or not. Okay. Anyway, the residual standard error, basically the square root of your residual sum of squares, or your average residual sum of squares, you're dividing by n minus 2. That's going to be kind of how much the response deviates from the true regression line, which we don't really know, but we're hoping, okay? And then we have this concept of r squared. The r squared tells us the proportion of the variance in y that is explained by the regression model. And, in general, we want more r squared, okay? And r squared, you can take this as basically RSS divided by residual sum of squares divided by total sum of squares, okay? And you can do 1 minus residual sum of squares divided by total sum of squares, or you take total sum of squares minus residual sum of squares divided by total sum of squares. So the proportion of the total sum of squares that is explained by the model. So that is not your residual sum of squares, okay? And if you have simple linear regression, it's equal to just your correlation squared. As you add more things, it gets a little bit, it's still this idea of residual sum of squares. How much is explained by the model. So just to kind of illustrate this value of r squared, I'm going to fit this very, very simple data set, 4 data points. X is 1, 2, 3, 4. Y is 2, 6, 4, 8, right? So the points 1, 2, 2, 6, 3, 4, and 4, 8. And if you calculate the correlation between X and Y, you get a correlation of 0.8. And if you calculate what's the linear model between X and Y, you'd get a slope of 1.6 and an intercept of 1.0. Slope of 1.6 and an intercept of 1.0. And so if you plug that in, okay, this is our X and this is our Y, and this is our Y hats, right? So again, Intercept of 1, slope of 1.6. So if x is 1, my prediction is 2.6. X is 2, my prediction is 4.2. My prediction is 5.8. My prediction is 7.4. Okay? And that's what this red line represents the fitted line. And these orange lines represent the residuals between the actual value and the fitted line. So the actual value is 2, the fitted line was 0.6. The actual value is 6, the fitted line says 4.2. The actual value is 5.8. I'm sorry, the actual value is 4 and the fitted value is 5.8. Actual value is 8 and the fitted line was 7.4. So the orange lines represent the residuals. What is the concept of total sum of squares? The total sum of squares is, well, if we didn't have a prediction line, what value would we predict for everybody? We would just predict the mean of y. So we'd take 2, 6, 4, and 8. We'd say, what's the mean of these 4 values? The mean is 5. Okay, y bar 5. And so here, I would just predict 5 for everyone. And so having the model greatly reduces the difference between our prediction of 5 is now goes from 5 to 2.6, right? So my total sum of squares here, we have a difference of 3, okay? Over here, my the actual value is 6, and without a model, I would predict 5. I have a residual of 1, or here, the actual value is 4, my predicted value is 5, I have a residual of 1. The actual value is 8, my predicted value is 3, residual of 3. And if I square those sum of squares, we get 20. Okay, so that's my total sum of squares, and that's the green lines. The green lines is the difference between using the mean for everybody, and if we square all of those, we get a total sum of squares of 20. If I calculate the residual sum of squares, and I take the difference between the actual and the predicted, okay, here the difference is 0.6, I square that, I get 0.36. The difference between 6 and 4.2 is 1.8. 1.8 squared is 3.24. And if I square all of these things, 1.8 squared and 0.6 squared, I get a residual sum of squares of 7.2. Okay? Is that okay? The difference between the green lines and the orange lines, this representing the total sum of squares, this representing the residual sum of squares. So how much of a reduction do we have going from 20 down to 7.2? Well, your r squared value is going from 20 down to 7.2. And what kind of percentage reduction is that? 64% reduction. That's your r squared value. To go from 20 down to 7.2 is like a 64% discount on your sum of squares. Okay, so 20 minus 7.2 is, whatever this is, 12.8. Okay, and you divide that by 20, you get 0.64. Okay, and that is your r squared value. Your big r squared value, 0.64, that for simple linear regression is also equal to 0.8 quantity squared. Okay, and that's where we're getting this concept of r squared, total squared, being reduced down to RSS, residual sum of squares. Let me give you your second view quiz answer. Today's second view quiz answer is C. C as in cat. C as in cat. Okay. All right, any questions here? We feel okay? Okay. Let's keep going. And so now we want to bring in more variables with multiple linear regression. So in multiple linear regression, we have multiple predictor variables. So not just one x variable, but we have an x1 variable and an x2 variable and an x3 or whatever, however many you have, okay? Up to your p predictors. And so now, when we make a prediction, I'm sorry, these should have hats all over them. I apologize. Pretending these all have hats. I apologize. I left them off. I'll have to fix that. Okay. Hats. Your estimated hats, estimated coefficients, those get used, and we plug in, whatever you have. Those are your fitted values. Oh, and I'm missing the hats again. Okay. Sorry, I gotta go back and put hats on everything. All right, we estimate the coefficients same way, okay? We try to minimize the residual sum of squares, the difference between the actual values and our predicted values. And again, this is not 100C, so we're not gonna go through the that process of deriving our coefficient estimates, but matrix, and I think in 100C you can solve this using partial derivatives for each of these things, or you can do it in matrix notation, and you get the same answer. The diagram here says, okay, what if we have two predictors, x1 and x2? The red dots represent the values that we have, and now our linear model, if we have two predictors, our linear model is a flat plane. Okay, it's a flat plane into if we have two predictors, x1 and x2, and you can imagine it's hard to visualize, but in higher dimensions, it's still kind of this linear plane. It becomes a hyperplane in this higher dimensional setting. It's still a flat surface, so there's no curvature here, right? We don't have any kind of curved shape here. It's just a flat, a flat plane floating in this dimensional space, because it's, again, linear model. We're saying if x1 goes from 1 to 2, it has the same effect as x1 going from 100 to 101 to 102. Same thing with x2. If x2 goes from 2 to 3, it's going to have the same effect as x2 going from 1002 to 1003, an increase of 1 or something. So it's going to just be this flat surface, and we're trying to find what is the correct way to angle this surface, basically this wooden plank. What's the correct way to angle this so that we're minimizing these squared distances, the squared residuals, the red dots from the plane? So that's what we have. Okay, we have kind of these knobs here, right? So now earlier, I think one of our very first slides, we said, okay, well, let's look at the relationship between TV, radio, and newspaper and sales. Now here we fit three separate simple linear regression models. We said, what's the relationship between TV and sales? What's the relationship between radio and sales? And what's the relationship between newspaper and sales? And we could say, what if I just fit three separate models, three separate linear regression models, and then I just add them up and then I divide by 3? Couldn't that work? Okay, or something like that. Well, let's just take a look at what happens here. Okay, and so here, using tidymodels, I'm going to take the linear regression model and I'm going to have 3 different fits. Okay, I'm going to take the linear model and fit sales to TV. That creates my TV fit. I'm going to fit sales to radio. That creates my radio fit. I'm going to fit sales to newspaper. That creates my newspaper fit. And then I'm going to extract. Basically, this is I'm going to call summary, and I'm going to just extract the coefficients table, and I'm going to round it to 4 decimal places. That's what this command is. So let me just kind of compare back to this output. Okay, so this is the output when you call summary on a linear model. Our output's this stuff, right? It creates a call. It gives you a 5-number summary for the residuals, your min, max, and your median. And it also gives you this table for your coefficients. Okay, and by using tidymodels, I'm saying I just want to look at this table here. I just want to look at this table, the coefficient estimates, and basically the relevant, test statistic t and the p-values associated with those things. Okay, that's what this part does. Okay, so we're going to take our TV model fit. We're going to extract the fit engine. We're going to apply summary to it, and from that summary, we're going to extract out the coefficients table. That's what this is, okay? So each of these things, I'm piping a bunch of these things. Now, the recommended style is every time you do a pipe, you put it on a new line, okay? To kind of keep it a little bit easier to read. For the sake of fitting it all on the slide, I'm using poor style, and I'm putting all of my pipes in one line, okay? That's a little bit harder to read, but just for the sake of fitting them on one slide, that's what I'm doing. But the recommended style, as you read your textbook, you're going to see every time there's a pipe, they go to a new line. And I kind of recommend that as well as you're doing your homework. You have the luxury of vertical space. On my slides, I don't have as much vertical space, right? So I'm piping it into coefficients to extract that coefficients table. And then default R, keeps a whole bunch of decimal places. And so here I'm just saying round it off to 4 decimal places. And that just, again, just makes it easier to read on a slide, not necessarily what you should do in your homeworks or anything like that. Okay, so here, this was, these are the same kind of results that we saw in that summary table. We got the slope of 0.0475, the t-value of around 17.6, compared to the standard error. And our p-value for all intents and purposes is 0. I think it was like 1 times 10 to the negative 16, okay? So we get a p-value 0. We check what's the relationship between sales and radio, okay? Here we get a slope of 0.2. We get a test statistic of 9.9 or something, and p-value of practically 0, okay? And this is interesting. Our radio is actually, as far as the impact per dollar spent on radio, is actually, close to 5 times higher, or 4 times higher, a little more than 4 times higher than that of the impact on TV, right? So radio might be a cost-effective medium or something, okay? And then we also say, okay, what is the effect of newspaper on sales? And we get a p-value not as dramatically low, okay? We get a test statistic of 3.3 and a p-value of 0.001, okay? Still, these are all significant at the 1% level, okay? Certainly significant at the 5% level, significant at the 1% level. And so if we fit any of these things, we would say, oh, okay, all of these things are significantly different from 0. All of them have some kind of role in the advertising money has an impact on sales figures, okay? However, what if I create a model where we're going to say, okay, what is the effect of sales, predict sales based on combining TV, radio, and newspaper. So we're going to have 3 predictors now. This is the multiple linear regression fit, okay? So this creates my combined fit. And now let's extract just that coefficients table this time, okay? What do we get here? We get a t of 0.045, a radio coefficient of 0.188, and a newspaper coefficient of negative 0.001, okay? And when we calculate the test statistics here, okay, and the p-values, we get, okay, the p-value associated with the TV sales is very significant. P-value for radio is significant. P-value for newspaper is 0.86, indicating that we don't have evidence that it is significantly different from 0, right? And so there might be a little bit of confusion here, okay? So what's going on? Over here, we have evidence that newspaper, there is a significant relationship between newspaper and sales. Whereas when I do the multiple linear regression, now I no longer have evidence that there's a significant relationship between newspaper and sales. Okay, so what's the, how do we explain what's happening here?
Go back to the
Yeah, so here there is a significant relationship between newspaper and sales, right? So these are, we said predict sales based on TV, predict sales based on radio, predict sales based on newspaper, okay? And according to predicting sales based on newspaper, there is a significant relationship. Okay, maybe not as dramatic as these other ones, but there is a significant relationship. Whereas when I fit multiple linear regression, it's no longer significant. Yeah, what's going on?
Is there potential collinearity between variables?
Yeah, so there could be collinearity between the variables, or basically just the fact that there's correlation between variables will cause your data to appear to have relationships when there's no real relationship. Okay, so so if we look at just the correlations between our variables, we can see there is a correlation between radio and newspaper values. Okay, it's not huge, but a correlation of about 0.35. Okay, so this I'm just quoting directly from the textbook here. Okay, it says notice the correlation between radio and newspaper. It's 0.35. So what this indicates is that markets where we have lots of newspaper advertising also tend to have high radio advertising. Okay, and so let's assume that this multiple linear regression is correct, that newspaper does not have an impact on sales. Okay, but radio advertising is associated with sales. Okay, so in markets where we spend more on radio, our sales will tend to be higher, and those also will happen to be markets where we also spend more on newspaper advertising. And so if we're only looking at the relationship between sales and newspaper spending, okay, we're going to observe in those markets that, yeah, there's more sales and there's more newspaper spending, and so it's going to appear like there's a relationship, but it's not that newspaper actually is correlated to sales, but it's actually radio is correlated with sales. Radio advertising is correlated with sales. And it just so happens in our data that radio advertising, markets where we spend more on radio are also markets where we spend more on newspapers, right? And so, you know, in, I don't know if you've taken 101B, some of you yes, and some of you no. In 101B, when you're designing your experiment, you try to set up your levels in such a way where you don't have these kind of correlation between predictor variables, right? You try to make sure your predictor variables are orthogonal to one another so that you don't end up getting correlations and you know have these kind of confounding situations. Okay, but in observational studies where you don't get to set up your experiment, you don't get to ensure that all of your predictor variables are orthogonal to each other, then this kind of stuff could happen. Okay, and that's why multiple linear regression is important to kind of consider all of these relationships at once rather than just one at a time. Okay, and you know, the kind of this classic example of correlation and causation and things like that. You know, does the rooster's crow cause the sun to rise? We know that's not the case, and you know, there's the relationship doesn't work that way. But that's what we have. Okay, so according to multiple linear regression, newspaper is not correlated with sales. And so even though simple linear regression seems to indicate that there is a relationship there, it's just the fact that newspaper is related to radio. Radio impacts sales, or maybe not impacts, but is correlated, has a significant slope to sales, and therefore as kind of a side effect, it's going to appear that newspaper is also related. Okay. There is, so back here, when we used tidymodels, okay, we specified, okay, fit the data using this formula, sales to TV, sales to radio, sales to newspaper, and things like that. When we use tidymodels, if we know we're going to fit a whole bunch of models, we can create something called a workflow. Okay, and a workflow, and we will get more into this on Friday. Okay, we'll talk more about workflows, but I just kind of want to introduce this here. And if you don't understand every single line of code in today's slides because I don't go into the explanation, that's okay. All right, but I just want to kind of introduce this concept of a workflow. Okay, because as you fit a bunch of data, a bunch of statistical models to your data in this process of exploring and trying to find a correct model, you end up finding that you have to do like similar functions and similar things, and among those things is some processing, feature engineering, right? So I think one of my later slides talks about okay, maybe not. What do you do if you have a categorical variable and you want to include it in a linear regression model? Okay, what do you guys do in 101A if you have a categorical variable?
Oh, create a dummy variable.
Create a dummy variable, right? So you take this thing and you can say, let's say this is a categorical variable that it only has 2 categories, yes or no, right? Is the person a student or not? Okay, and you can say if the person is a student, we're going to make this thing a 1, and if they're not, we make it a 0. Okay, and that's one way to kind of create a feature or a variable that can be used in your linear regression model. And you'll have kind of like in cases where the person was a student, you add this number, okay, or or something like that. Okay, and if you have a categorical variable with more than more than 2 categories, then you're going to have multiple dummy variables, right? You're going to have to say, okay, if the I don't know what categories we're going to have here now, but we're going to say, if the person is from California, they get this variable. If the person is out of state, they're going to get this variable. If the person is international, they're going to get this variable or something like that, right? So I think that's how the UCs kind of classify its students. It says in-state California, California resident, out-of-state domestic, and out-of-state international type of things. And you're going to have to say, okay, so one of these will, you'll have 2 dummy variables now. One for international, yes or no. One for out-of-state, yes or no. And if both of those things are no, then that means they're California or something like that. And so you find out you have to kind of do this kind of processing of your data, and then you have to fit your things. And so it makes sense to create this thing called a workflow. And in creating those dummy variables goes into this process called recipes, and we'll get into all of that. But the very basics of this is you create a you create a parsnip model object, okay? So here we're going to say, let's make a linear regression model. We're going to set the engine here, okay? And so this is a parsnip model object using the package parsnip, and this is the LM model. And then as far as our workflow goes, we're going to just establish an empty workflow. And to this workflow, we're going to add the linear model object to it. Okay, so we're going to say add a model, and this is the most basics of workflows, and this is a linear model workflow. And from here, we can then take this workflow and we can run it through different model scenarios, okay? And so here, what I'm going to do is I create a list. This is going to be a list of different formulas that we want to run this linear model workflow through. Okay. So we're going to say, create a TV model where we're going to predict sales based on TV. Create a radio model where we're going to predict sales based on radio. Create a news model where we predict newspaper model where we predict sales based on newspaper, right? So this is all gathered in a R list. I've got a series of formulas here. Okay. Now, to do this, I take, we're going to create a workflow set. Okay. So I take my list of formulas, and I'm going to create a workflow set. And again, don't worry about all of this right now, but we're going to say, all right, we're going to create a workflow set called advertising models, and we're going to basically run the linear model and run it through our formula list. And so what this is going to do is now I've got a workflow set, okay, which contains 3 rows, and within the row there's a column called info, and it's information about each kind of workflow that we've created. And the column itself, the value in here itself is a tibble, okay, is basically a table inside of this. So it's a little bit of a confusing data structure. So this larger data structure is a table with 3 rows, but within this cell I've got like another table. It's like a little miniature table here, okay? But it's not a miniature table. It's a full-blown table, right? So we're going to say, okay, well, what if I go into this column? Let's just pull out, what is this table here? So it's a tibble 1 row 4 columns, okay? So it says, okay, well, let's look this up. So I say, okay, what is models, column info? Give me the first thing in there, okay? So it says, okay, that's a tibble 1 by 4. And so here we get another tibble. And it says, okay, your first column is the workflow. Then you've got your pre-processing, which is kind of this formula. The model is the linear regression model. Are there any comments? No comments. Okay. So what is this thing? Workflow. Okay. So we go into this and I say, what is this workflow? And the workflow itself, this is kind of just the output of what a workflow looks like. And it says we're doing a linear regression model. The formula for the pre-processing says we're going to predict sales based on TV, and the computational engine is LM. So it's kind of all of the kind of the information that we've done. Oh, you can't read this. Okay, I'll have to fix this as well. Okay, so basically, I'm going to run a fit. I'm going to create a column called fit into this workflow set. Okay, or I'm going to create a new data frame called or tibble with the results, and we're going to create a column called fit, and I'm going to map onto this column info. We're going to go through basically each of these things which contain information about the workflow. We're going to say take fit to that workflow. Fit that workflow to our advertising data, okay? And again, this line, it's kind of complicated. Don't worry if you don't understand it in today's lecture, that's okay. But I want to kind of introduce this idea of a workflow where you can specify kind of this overarching thing that you want to do multiple times. You give it a few different options, and then you kind of say, all right, here's this thing, now repeat it with all of these different options, because that's a thing that you often want to do, right? And this is kind of like a big headache. I don't know if you've tried to do I don't know if you participated in Data Fest, but you might have had all of these different ideas, and you say, well, I want to do this, and then I want to do this, but every single time you do it, it's like, oh, I've got to redo this, and you keep, you forget and you keep track. So having a nice workflow defined is nice, okay? And once we have that workflow run, we can take that results table that I've created. We can extract out each of the different fits, and we can pull out the coefficients and get the same kind of results that we had before. Okay, so this feels like a lot of work, and admittedly, for this small example, this is probably overkill to set up a workflow where you're just going to fit like 3 different models or something. But but we can see like, okay, but this will make it more efficient if you wanted to fit like a dozen different models, a dozen different specifications. And you can also incorporate the workflow to not only fit this thing, but then run it against your test set and get metrics right away. And you can start, once you have your workflow set up, you take the model specification, you run it, you train it on your training thing, and have it immediately run, test it against the test data, and give you the metrics. And right away you can see, okay, this is how well this performed, this is how well this performed, this is how well this performed, and you can start evaluating. So when you do multiple linear regression, going back to just this concepts of multiple linear regression, there's a few important kind of questions that we want to answer, and I kind of just copied a lot of the content directly from this chapter 3, and so there's a little bit too much to fit in one lecture here. So I want to just kind of make sure that as you do your homework, that you will take the time to read. Read as much as you can of chapter 3 and linear regression, and especially if it's been a while since you've done 101A and you've forgotten some of these things. I think it's worthwhile to spend time on it, and otherwise, if you feel very comfortable with kind of the 101A concepts, then maybe it's a little bit less important, right? So, the first question is, at least one of the predictors useful in predicting the response. That's kind of like your overall model, right? So when you take the model where you fit all of these three things, the overall test that's being performed is an F test, okay? Are any of these coefficients equal to 0 versus the alternative that at least one is non-zero? And you do kind of the F test, and you say, I used all of these extra degrees of freedom, and did it reduce the residual sum of squares and things like that? Okay, the number of predictors that you're including, and in this summary value, you get this F statistic of 570.3. And your F test, you have 2 degrees of freedom, so we have 3 predictor degrees of freedom because we have 3 predictors, and then we have 196 residual degrees of freedom because that's what's left over, right? We have a total of 200 observations, a total of 199 degrees of freedom for the entire thing, because we're comparing it against the null model where 1 degree of freedom gets used to estimate the mean. So 200 minus 1, 199 total. And if we're using 3 on the predictor, that leaves 196 for the residuals. And so when you do this, 570 is this ridiculously high number, so we get a p-value of practically 0, and that's what we have here. Okay, so it comes back and it says, yeah, at least one of these things is significant. Okay, and then we can kind of go through each of these predictors, and we can say, okay, you know what, this one was not significant. Okay, and so then the next part is, well, how do we select the models or select the variables to use in our final model? And I think this would have been covered in 101A. Is you have the kind of these 2 basic strategies. One is forward stepwise variable selection, where you start off with the empty model and you're going to select one variable at a time, right? So you start off with the empty model, and in our case we have 3 potential variables to choose from. So we do simple linear regression with TV, simple linear regression with radio, simple linear regression with newspaper, and we say which one of these was most significant. Oh, TV was. Okay, so we add that in, and then now we look at the remaining variables. So we're going to do, so now we have a model where we use TV, and we say, okay, what if I do TV plus radio or TV plus newspaper? Okay, which one produces, has better performance with the RSS? And then you kind of keep adding variables in that way until you get a model where you can't add any more variables without, add any more variables that are significant. Okay. backward selection works kind of the opposite. You start with the model where everything's in there, and then you say, okay, well, let's remove this one, which is not significant. Okay, the least significant of these things. Okay, and then once we do that, let's remove the next one that's least significant, and we keep doing that until all of the variables that we have left are significant. Okay, and then you have this mixed process where you kind of do forward selection, but sometimes when you add a variable, it makes other things less significant, and then so you remove a thing, and you kind of have this kind of forward and backwards process until you arrive at some kind of subset of variables where they're all kind of significant and you can't add anything more. Okay, these things, assessing model fit. So as you read this, you can assess your model fit. R squared is kind of our default measure to assess model fit. But one issue is that the R squared value always goes up as you make your model more and more complicated. Okay, and so as we select more variables, if we're driven only by R squared, okay, it could lead to bad models. And so again, we're going to see if any of our coefficients are significant. Again, this is kind of your classical approach to multiple linear regression. And we can use R squared to see how it performs. And again, what we'll do in our course is we'll use the training data and the test data or cross-validation during kind of the training and assessing phase to see how well our models perform. Okay, so not just R squared, your traditional things. 101A, you also learn, your AIC and your BIC measures for which apply different kind of penalties for having too many predictors and things like that. And you have these different tools to assess fit. And the key is you don't want to use any one of these tools just completely blindly either. Okay. And then lastly, we can use our models to make predictions, and I'm going to point you to making predictions using parsnip. And basically, once you have your models created, you can just use the predict function and your test data set. Okay. And that makes it quite easy here. Let me go ahead and give you your last view quiz answer. And today the last view quiz answer is the letter E. E as an elephant. E as an elephant. We'll just end a little bit early today. Okay. Maybe 15 minutes early today. So we'll end lecture here. I've posted homework too. And, kind of one thing about summer is we're covering a lot of content in a short amount of time, and you have to do a lot of kind of reading to kind of keep up with the stuff. So please make sure you do the reading that I've assigned in the homework. And with that, we'll end here for today, and we'll see you guys on Friday.